Hello and welcome to our second thermodynamics presentation, number 5 overall, looking at specifically spontaneity having to do with entropy, what we briefly did introduce last time. All right, so entropy, thermodynamic function that increases as the number of energetically equivalent ways of arranging the components increases, or S. S is generally joules per mole Kelvin. Now, delta H, kilojoules per mole, entropy, joules per mole Kelvin. So keep that in mind, they have different units. Now, energetically equivalent ways of arranging components. What is that? Well, think about a classroom. 35 desks, one student. How many ways, how many different positions can one student sit in 35 desks? 35. Now take the same 35 desks, but let's say you have two students. How many different combinations can you have two students sitting in 35 desks? A heck of a lot more. And so forth and so forth. So it comes down to the arrangements or the organization of the sample. It comes of the molecules, the atoms, whatever you're dealing with. Random systems require less energy than ordered systems. Well, think about it. If your room's a mess, it's very easy to make your room messy. You just don't put things away. You are lazy. You come home from school or whatever you did, you throw your jacket down, kick your shoes off, throw your socks hanging on the ceiling from your fan, whatever it is. But in order to have an ordered system, you'd have to walk into your room, take your jacket off, put it on a hanger, hang it up in your closet, put your shoes away, you take your socks off, put them into your hamper. Much more effort involved with an organized or ordered bedroom. So entropy lends itself to being less ordered, chaos, anarchy. It's just easier to do. It's less energy to be in that state of being. That's what it goes towards. The driving force for a spontaneous process is an increase in entropy of the universe. The second law of thermodynamics, the entropy of the universe, is constantly increasing. So any spontaneous process that occurs is going to add its entropy to the universe overall. So spontaneous things are just following the second law of thermodynamics in increasing the entropy of the universe. Nature proceeds towards the state that have the highest probabilities of existing. So it's just nature wants to force things to be in a position that is the most stable. In order to be the most stable, you have a lower amount of energy. So nature proceeds this way, and you can't really fight natural law. I mean, you can, but you're not going to win. So it goes along with the fact that this is what nature does. This is what's going to happen. So whatever process you are looking at, whatever reaction is occurring, it occurs in such a manner to go along with what nature wants it to happen. It puts it into a position of the highest probability of occurring. So positional entropy, which is kind of one of our ways for us to determine, are we having an increase in entropy or a decrease in entropy based on a written reaction? The probability of occurrence of a particular state depends on the number of ways in which it can be arranged. So if you look at a solid, look at the structure of a solid, and then look at the structure of a liquid, and then look at the structure of a gas. Yes, there are two greater than symbols from liquid to gas on purpose, because the increase in entropy going from a liquid to a gas is that much greater compared to going from a solid to a liquid. So ice melting to a liquid has an increase in entropy, but a liquid boiling, turning into a gas, has a greater amount of entropy. In a solid, it's nicely organized, it's a crystal structure. It takes a lot of energy or a lot of entropy to organize itself that way. Liquid, still kind of organized. The molecules are close enough, but they're moving around, they're sliding around each other. But as a gas, it's complete chaos. Everything is going everywhere within the sample and within the container or in an open container, everywhere. So you can see that the organization goes down very quickly from a solid to a liquid to a gas. Similar to the example that I gave having to do with students sitting in a desk or the number of desks in a room, here's your microstates. We have 6 different particle arrangements that result in the same macro state. So the macro state is the 2 round bottom flasks connected. There are a total of 4 atoms. We number the atoms 1, 2, 3, 4. Well, there's only 6 different possibilities to arrange 4 atoms that have an identical state. So one student sitting in any one of 35 desks, it's the same macro state, one student, 35 desks, but it's 35 different microstates. Any questions on macro versus micro? So changes in entropy, or delta S. Final minus initial. Products minus reactants, same idea. Entropy is favorable when the result is a more random system. So we want positive entropy. An increase in entropy is more random, more chaos, less organized. Some changes that increase entropy, pretty straightforward. Reactions whose products are in a more random state. So solid to liquid, liquid to gas, solid to gas. Anytime you're going to the right from solid, liquid to gas. Larger number of product molecules. So looking at your coefficients. Are you going from 2 total moles of stuff to 4 total moles of stuff? But please realize, if I go from 2 moles of gas molecules to 37 moles of solid, gas still has way more entropy than does a solid. So you got to kind of look at reactions as a whole. You can't look at it as states only. You can't look at it as coefficients only. You got to kind of keep the two together, looking at them simultaneously and seeing what's going on as a whole. Increase in temperature. Well, think about it. What do molecules and atoms and things tend to do when you increase the temperature? Yes, they start vibrating more. They start moving around more, moving faster. Realize vibrational movement and transitional movement. All those things count as entropy. So take a water molecule, for example. The hydrogens on either side of the oxygen are not always the exact same bond length. The hydrogens, one goes in, get closer to the oxygen, one gets further, and vice versa. They're rotating, they're vibrating, lots of different movements. So increase in temperature is always going to increase your entropy. Solids dissociating into ions upon dissolving. So take sodium chloride, you put it in water, you're making pasta. You're boiling water to make pasta. Well, the dissolving process, while the solid, sodium chloride, it's a solid. It has very low entropy. But the minute the bonds break and the ions are free of their lattice structure, they're now individual ions. That's going to increase the entropy going from solid to ions. Now, please make note, we are not talking about the entropy of the solution that has been made. We're talking about the entropy going from a solid dissolving into ions. There is a difference, which will come up soon. All right, second law of thermodynamics, what we did I hinted at earlier. The second law of thermodynamics says that the total entropy change of the universe must be positive for a process to be spontaneous. So for a reversible reaction, delta S of the universe is 0. Because there's no net change in entropy, you're not becoming more or less organized. For irreversible processes, spontaneous, like we saw before, the universe is always going to be positive. So we know that entropy of the universe has to be system plus surroundings. If the entropy of the system goes down, then the entropy of the surroundings must go up by a larger amount. So even though the system may be decreasing in entropy, the surroundings will increase by more to keep this equation true. Delta S of the universe is always increasing for a spontaneous process. If entropy is decreasing in the system, does not necessarily mean it's not a spontaneous process. When the system is negative, the surroundings must be positive and big for a spontaneous process. So the same thing we kind of just said. Ultimately, the second law of thermodynamics has to hold true. You can't, the system and the surroundings both cannot be negative for this to hold true. All right, so how do we kind of quantify this and put some numbers behind it to maybe back it up and support the second law? The entropy change in the surroundings is proportional to the amount of heat gained or lost. So enthalpy is going to play a role. We know that the heat of the surroundings that it gains has to equal the heat the system lost. So it's still an endo-exothermic process. Whatever the system is, the surroundings will be the opposite. The entropy change in the surroundings is also inversely proportional to its temperature. At constant pressure and temperature, we get an equation such as this. The entropy of the surroundings, or change in entropy of the surroundings, is equal to the negative delta H of the system over T. So we can see the direct relationship between entropy of surroundings and delta H, and the inverse relationship between delta S and temperature. This type of equation is not part of your equation sheet. It is not going to be asked to be solved on the AP Chem exam. However, the relationship needs to be known and understood. Questions? So, a couple of other things to look at when we're trying to figure out, is entropy increasing or decreasing from a conceptual standpoint, not mathematically. We already know this to be true. Solid is less than liquid, which is way less than gas. So looking at water versus a liquid and water versus a gas, you can see a pretty big difference there in the entropy. Molar masses. The larger the molar mass, the larger the entropy. Looking at the noble gases, you can see as they get bigger, there's more space for the electrons to move around, more going on. The entropy is going to be larger. Bigger atom, things can be dispersed better, and it ultimately is going to have more entropy for a larger molar mass element or compound. Complexity. So how many atoms are even in the compound? Larger, more complex molecules generally have larger entropy. Argon versus nitrogen monoxide. Argon may be bigger from a molar mass perspective, but you have 2 atoms in nitrogen monoxide. It's going to have more entropy because you have a bond involved, and that bond has movement. Any more movement is going to add entropy. More energy states are available, allowing for more dispersal of energy. Here's carbon monoxide versus C2H4. Pretty much the same molar mass. Not enough to make a big difference, but you can see there's a larger difference in the entropy. More bonds, more things going on, plays more of a role in the entropy. Dissolution, so things dissolving. Potassium perchlorate as an aqueous ions versus potassium perchlorate. Perchlorate. No, not perchlorate, just chlorate. Sorry, Potassium chlorate aqueous versus potassium chlorate solid. As aqueous ions, it's going to have greater entropy. Dissolved solids generally have larger entropy, distributing the particles throughout the mixture. So again, solid to aqueous. From our solid to liquid to gas scale, the aqueous would kind of fit in between liquid and gas, but not directly in the middle, more towards the liquid side than it would on the gas side, to give you a reference point. All right, we've looked at a bunch of different things conceptually that help us decide if the entropy is increasing or decreasing, and thereby you can figure out on positive entropy, you're spontaneous. On a decrease or negative entropy, you are not spontaneous. All right, standard entropy change. We know that it is, or represented by, the difference between absolute entropy between the reactants and products under standard conditions. Absolute comes into play because look at the unit again. Joules per mole Kelvin. Entropy is based on the Kelvin scale, not Celsius or the F word. We never say the F word. So similarly to enthalpy, you saw the same equation, products minus reactants. So you can look up entropy values, or you're given entropy values. But a couple things to remember here. Standard enthalpy of formation of an element is 0 kilojoules per mole. The absolute entropy at 25 degrees is always positive, meaning if you have an element in its elemental state, it has entropy. It does not have enthalpy of formation. Question? Thank you.